The main job of the lungs is gas exchange, pulling oxygen into the body and getting rid of carbon dioxide. Normally, during an inhale, the diaphragm contracts to pull downward and the chest muscles contract to pull open the chest, both of which suck in air like a vacuum cleaner. And then during an exhale, the muscles relax, allowing the lungs to spring back to their normal size, pushing that air out. Now, we can use a spirometer to measure the volume of air that moves in and out of the lungs with each breath, in a test called spirometry. Now, currently, there are more sophisticated electronic spirometers, but a classic example is having an air chamber submerged in water that a person can breathe into. As they take air in, the chamber moves down into the water, which moves a pencil that traces a line. Then when they breathe out, the chamber moves back up and the pen moves down. So if this is a healthy adult female, as she breathes, the spirometer makes a wave-like tracing on the paper. The plot you end up with has volume of air on the vertical axis, and the horizontal axis shows time. During normal, quiet breathing, the volume of air moving in and out with each breath is represented by the height of the wave, and it's called the tidal volume. And this is typically around 0.5 liters or 500 milliliters. After a few cycles, we might ask her to inhale the maximum volume of air that she can, and then exhale the maximum volume of air that she can. The volume of air that she maximally inhales above the tidal volume is known as the inspiratory reserve volume, and it's typically around 3 liters. This is sort of like a massive backup capacity that you don't typically use, but might need to in a specific situation, like if you're going to dive in an ocean. Similarly, the expiratory reserve volume is the volume of air that she maximally exhales below the tidal volume, and this is typically around 1.2 liters. Now, even after she attempts to exhale all the air from her lungs, it turns out that there's still some air in the lungs, and this is known as the residual volume, and it's typically around 1.2 liters as well. Combining the expiratory reserve volume and the residual volume together gives you the functional residual capacity, which would be about 2.4 liters. Similarly, combining the tidal volume and the inspiratory reserve volume gives us the inspiratory capacity, which is 0.5 liters plus 3 liters, or about 3.5 liters. Going one step further and including the expiratory reserve volume as well, you get the vital capacity at about 4.7 liters, which is the volume of air that can be exhaled after a maximal inspiration. So inhaling all the way in and then exhaling all the way out. Finally, adding the vital capacity and the residual volume, you get the total lung capacity, which is the total volume of air that the lungs can hold, which would be 4.7 liters plus 1.2 liters, which based on what we have is 5.9 liters, almost 6 liters. Finally, keep in mind that all of these lung volumes that we just calculated are considered static lung volumes, rather than dynamic lung volumes, because they don't involve the rate of airflow in and out of the lungs. Now, even though we said that the typical residual volume is 1.2 liters, if we were using the spirometer as it's set up, it wouldn't actually be possible to figure this out, since the residual volume is the amount of air that a person can't exhale even when they try. But this residual volume can be measured using something called the helium dilution method. With this method, a known concentration of helium is placed into the spirometer to breathe in, written as concentration C before. And we also know the volume V of the spirometer, V spirometer. So to find the total mass of helium, M, you just multiply the concentration times the volume, C before times V spirometer. Since units are milligrams per milliliter times milliliter, that equals milligrams, or the mass of the helium. Alright, so next the person's asked to breathe in the helium mixed air. The helium is insoluble in blood and lung tissue, so that helium stays in the lungs and within a few cycles of breathing is redistributed equally between the spirometer and the lungs. At that point, the person exhales normally, which means that now the volume of air in the lungs is the functional residual capacity, or FRC. And then you've also again got the volume in the spirometer, V spirometer. Neglecting this small volume in the trachea, the total volume after must therefore be equal to the volume of the spirometer plus the FRC. At this point, the concentration of helium in the air, which has now been equilibrated between the lungs and the spirometer, can be called C after. So just like in the first system, you can take concentration C after times the new volume, V after, and get the total amount of helium. Since we didn't actually change the amount of helium in the system, M helium is the same as it was at the start. And so this means that these two equations can be combined to be concentration before times volume of the spirometer equals concentration after times the sum of the volume of the spirometer and the FRC. The concentrations of helium before and after can be measured, and the volume of the spirometer is known, so that leaves only the FRC as the unknown value. So at this point, it's just a matter of plugging and chugging. So let's say the spirometer has a volume of 300 milliliters, and we put some helium in the spirometer and measure the concentration, and it turns out to be 0.54 milligrams per milliliter. Now, when the person's connected to the spirometer, let's say that the concentration of helium is measured to be 0.06 milligrams per milliliter, after the person exhales normally. Now we can solve for FRC. 0.54 times 300 equals 162, which equals 0.06 times 300 plus FRC. And so 162 divided by 0.06 minus 300 equals the FRC, which ends up being 2,400 milliliters. Now, remembering back to our crazy plot of capacities and volumes, FRC is equal to the expiratory reserve volume plus the residual volume. Simple spirometry gives us an expiratory reserve volume of 1.2 liters. So, therefore, the residual volume is 2,400 minus 1,200, which is 1,200 milliliters, or 1.2 liters. Alright, another way of measuring the FRC involves body plethysmography. In this technique, a person sits inside a plethysmograph, which is an airtight box. The air pressure and volume of the box, as well as any changes in them, can be measured. So let's call the initial values P box 1 for the pressure, and V box 1 for the volume of the box. Now, Boyle's law states that the pressure times the volume of any gas is constant at a given temperature, or K for some constant in the box. So now the person is asked to breathe in and out through a mouthpiece which measures air pressure in the mouth. That mouthpiece is remote controlled and is closed to the outside world right after a normal exhalation. At this point, the pressure is measured as P mouth 1. And since they just exhaled, the air in the lungs must be the FRC. So at this point, the pressure in the mouth times the volume in the lungs, or FRC, is equal to another constant. Next, the person is asked to try inhaling. As they try, the lungs expand a tiny bit, but no air can actually come in since this is a closed system, and therefore the pressure in the lungs decreases. Here's the crazy part. Since that person and the box are in a closed system, these changes cause an increase in pressure in the box, as well as a decrease in volume of the box. Like the volume of the box actually decreases a tiny bit. And both of these can be measured. So the new pressure in the box is P box 2, and the new volume of the box is equal to the original volume V box 1 minus some small change in volume delta V. And from this, since we know everything else, we can solve for the small change in delta V. Sweet, so if we apply Boyle's law to the mouthpiece now, the pressure is P mouth 2, and the new volume is the original volume FRC plus that small change delta V. Since again the pressures are known, and now delta V is known, the only thing left to solve for is the FRC. Now normally the FRC you get from plethysmography is equal to the FRC you get from helium dilution. But if a person has an obstructive lung disease, then the FRC from plethysmography ends up being slightly more than the FRC from helium dilution, since that helium doesn't diffuse into every part of the lungs. Alright, as a quick recap. Some common lung volumes include the tidal volume, inspiratory reserve volume, expiratory reserve volume, and the residual volume. Every other measure is a combination of these four. Calculating the residual volume is tricky, and can be done by first calculating the FRC, which is done using either the helium dilution method or body plethysmography. What's up, guys? Thanks for watching that video on lung capacities and lung volumes. I know we got a little into the weeds with the equations there for a second, so hopefully you were able to follow along. I know myself, I was a little mind blown by the whole decreasing volume of the plethysmograph thing. So I thought that was pretty cool, and hopefully you thought that was cool too. So if you want to do a deeper dive into this topic, you should for sure head over to osmosis.org, where we've got a ton of flashcards and quiz questions and a bunch of awesome tools that are really helpful for you if you're a student in the medical field. So definitely check that out if you're interested. Otherwise, you can always support us by donating on Patreon, subscribing to our channel, and following us on social media. This particular video is written by Debal and edited by Rishi. I did the illustrations and the voiceover, and Yifan did the video editing. So thank you, everyone. Hopefully you have a good day. See you later.